Okay, so I think it's about time. Welcome back to DSP. So today is our final lecture before midterm. And as I promised last week, today's material will not be included in the first midterm. They will show up on the next midterm, which will happen in May. So today is really just let's take it easy. But regardlessly, today's material is quite important. Okay, so we will learn how to solve LCCDE, linear constant coefficient difference equations. Difference equations is the core topic of this course, and we need to learn how to solve them using Z transform, right? So here is a note. When we look at a difference equation, we interpret those equations not casually, causally. Okay, two very similar words. Causally, causal means casual. So please pay attention. We don't treat them casually. We should treat them seriously. But I mean, we interpret the equation by assuming that the impulse response is causal. Okay, well, we assume unless otherwise mentioned. Yeah. So maybe I can turn down the volume a bit. Yeah. Seems that we have a pretty large gain. Almost causing echo, so I will turn it down by 6 dB, seriously. There is a place I can turn gain down by 6 dB, if I remember how to set it. 6, now it's plus 6. Let me turn it to 0. Yeah, 0, okay, better. Okay, now it's better. It's more normal. Yeah. All right, so we will solve the equation by assuming that the impulse response is all 0 before time 0. That's what causality means. Okay, so with that, let's look at the general formulation. So generally, we have this. Yn, the output of the current sample on the left of the equation, and on the right, we perform linear combination. Okay, so there are two terms. The first term involves feedback, as you can see. We will look at the past samples up to m, big M, that many samples, and form a linear combination. So you see that this is something that we can be calculated. Then the second term is also a linear combination of the input from the current sample to up to n samples in the past. So in total, we look at n plus 1 samples in the past, input samples, and m samples of the past output, and we form a linear combination. We call this this is one line of computer code you can imagine, right? One line. So we can calculate the output given the past. Okay, so everything depends on the history. So far so good. Now we look at the history. Okay, and this system is obviously linear because there's no square term involved, right? We don't have any square inside the equation, so this is definitely a linear system. And we also assume that all the coefficients right here, I mean A and B, AK and BK, these are the coefficients, 系数. These coefficients are all constant, and therefore we call this equation a linear and constant coefficient difference equation. Okay? So to solve, so our task is to first realize that this equation gives you a linear and time invariant system. Okay? And we have learned that what is that one thing all you need to know about a linear time invariant system. All you need to know about LTI is the impulse response, right? Because the system is completely characterized by the impulse response in terms of convolution. So all you need to know, indeed, is the impulse response. Now we want to find out, okay? So if we agree that this equation characterizes a LTI system, then we need to find out, we want to ask, how do we find out the impulse response by some sort of calculation? Or how do we do that, okay? So there are a few steps, but first of all, the recommendation is to transform everything into the Z domain. Okay? transform both sides of the equation into z domain, from small y to big Y, from small x to big X. Okay, and then if we just organize our terms into y divided by big Y divided by big X. So last time I mentioned that we have introduced that the result is a ratio of two functions. The result is a ratio of two polynomials, to be exact. Two polynomials. Okay, so the first few words I may want to write down. Polynomial. That's it. So the result are two ratio of two polynomials. So in Chinese, the translation usually is 多项式. Two polynomials of z to the -1 power. Okay, two polynomials. So and we call the top polynomial b of z. The bottom, the denominator is a of z. Numerator, denominator. The numerator is b of z. The denominator is a of z. So that's our standard notation that we are going to be using all throughout the semester. Bz divided by a of z. Okay, so far so good? So that's from last time. So from here then, here comes the question. How do we calculate the impulse response of this system if we are given the coefficients? Okay, we're given this equation, how do we calculate the impulse response? And secondly, how do we ensure that the system is stable? Stability is an important thing. When we develop any kind of a system, we want the system to be stable. Okay, then you need to question, what do we mean stable? What's the definition of stability? That's a valid question. What's the definition of stability, right? So let me answer the second question first, okay? So the second question is that once we organize everything into h of z and let it be equal to, defined as y of z divided by x of z, and in turn it's going to be something like 1 plus, b0 plus b1 z inverse plus blah, blah, blah. B, if I remember, we have big N terms, z minus big N. And at the bottom, we have 1 plus a1 z inverse plus all the way to a, I remember it's up to big M, that many terms. So we have two polynomials, and we call what's on top b of z, and we call what's under there a of z. Okay, so that's our notation. Then the answer to stability. If you ask whether or not this system is going to be stable, the answer is rather simple. The conclusion is that we need to find out what's the root of a of z. Find out what's the root of a of z. Root 就是根啊，多项式的根啊。We find out the root of a of z. Okay, so in general, it's an nth order polynomial, so we should expect it will have m roots. Some might be multiple roots, 有些可能是重根. Some might be multiple roots, but in general, we have m identical or distinct roots. And we want to ensure that all the roots are inside the unit circle. Okay, that's the criteria for a system to be stable in a certain sense. Okay, but the conclusion is checking the root. You will check the root and to see if every one of them is inside the unit circle. If ZP is the root of A of Z, then we must have all of those roots should be inside the unit circle. Okay, the absolute value it should be within the distance of 1 from the origin on the complex plane inside the unit circle. That will guarantee stability, right? So that's the conclusion which will be clearer. The reason will be clearer why in the next couple of minutes, right? Any questions so far? Okay, so we will explain how generally to solve the impulse response by example, okay? So let's assume that our system is specified by this equation. this difference equation with yn on the left, and then we have two feedback terms with constant coefficient 1 and 1, and only simply one input term right there, okay? 1, 1, 1, and 1. Every coefficient is constant. Okay, so far so good? So this is an example, a very simple example of a constant coefficient difference equation. So by definition, so anyway, so quickly, if you follow this notation, very soon, one way or another, we realize h of z got to be 1 divided by 1 with a minus 1 sign here, the inverse, and minus 1 z to the minus second power, minus square, right? Is that all right? Because these coefficients, when we move it to the other side of the equation, this coefficient becomes minus 1, right? When we move this term to the left-hand side, this coefficient becomes minus 1 also. Therefore, we have a minus 1 here corresponding to this coefficient, and the minus 1 here corresponding to this coefficient. So everything's correct. And on top, we have only one single one term that corresponds to x of n, this coefficient. It's a 1 minus 1 minus 1, and that's why we get this result. Okay? Everybody with me so far? So hz, one way or another, you can convince yourself that this is indeed an expression for h of z. And the next step is also pretty straightforward. Now, find the roots. Okay? So we know that every polynomial can be factorized, factorized into a product of, in this case, we have a second power, we have a second order polynomial, right? So it has two roots, and we can factorize this polynomial into the product of two terms like that, where P1 and P2 are the two roots of this polynomial. Okay, so let's define our notation. I'm just going to copy everything on the board to right here. 1 minus z P1 z inverse. It becomes a product. 1 minus P2 z inverse. Okay. In principle, it's doable. And then here's a small here comes a small exercise. Then let's calculate exactly what is P1 and what is P2. Okay, that's the next. We need to figure out what is P1 and what is P2. So P1 and P2, if you will. So this is like 1. How do we start? P1 and P2. Okay, let me use this. P1 and P2 got to be, just so you can apply that simple formula for solving a quadratic form, right? Find the root. So 2 times, so if this is A, this is, no, let's say A equals to 1, B equals to minus 1, C equals to minus 1. Okay, that's the kind of the formula I have learned from high school. A, B, and C, right? So here A is 1, B is minus 1, C is minus 1. And the formula goes that the roots should be located at 2A under there. The top should be minus B plus or minus B squared minus 4AC, right? So that's the high school thing, okay? Really, that's a high school thing, okay? Yeah, you with me so far? That's a high school thing. So 2A, we have 2A and minus B, B is minus 1, so minus B is plus 1, right? Plus or minus square root of B squared is minus 1 squared minus 4AC. 4AC is 4AC. Seriously, this is how we go through the calculation. And if I remember correctly, so far we have P1 or P2. The two rows are located at 1 plus or minus square root of 5 divided by 2. These are P1 and P2. Okay, So that's a rather simple exercise. Okay? Okay, so let's from here. Um, from here, we are ready to move on to the next step. Okay, so we're gonna leave the result right there and jump to the next slide. Okay, so let's jump to the next slide and see. Now the next trick is a key step. The next trick is to reorganize h of z into a summation. Note that here we have a product, right? 乘法. We need to reorganize the product and perform a sort of a decomposition so that the result becomes a sum expression. Okay, change the expression. We need to the next step is a change of expression. Okay, still h of z. So having found out what P1 and P2 are, so in our case, now, for this example, we need to turn the expression 1 minus P1 z inverse 1 minus P2 z inverse, and we already know what P1 and P2 are, and on top we have 1. We need to turn it into a summation of 1, 2 terms. Big M is 2, right? Second order system. So we need to turn it into 1 minus P1 z inverse with an unknown. And this coefficient on top here is not known yet, okay? So it's unknown, alpha 1 plus 1 minus P2 z inverse. On top we have another unknown coefficient to be found out. Okay? Change the expression. We are going to change the expression, and this action is called partial fractional decomposition. Fractional, okay? Fractional decomposition. We decompose the expression into the sum of two terms, okay, for this example. And where now these two, the unknown coefficients become alpha 1 and alpha 2. Now the unknown becomes alpha 1 and alpha 2. We have calculated P1 and P2 already. That has been figured out. But what is unknown right now is alpha 1 and alpha 2. Okay? And why? So let's take one step at a time. Okay? So now, how do we determine alpha 1 and alpha 2? That's the next exercise. Calculate these two unknown coefficients for this case, for our special case. How do we do that? I can think of two ways of doing it, okay? The first way is more naive. So let's just highlight the naive way, okay? The first way is naive. Naive sometimes can be good. This is naive. Do you know what is naive? 天真的. The first way could be naive. The naive way is, let me see if this makes sense. Let's just put everything back to the product form. No. Put everything back to the product form, right? When we have two fractional components, and then let's merge them back together. And very soon you realize that on top we got to have alpha 1 times 1 minus P2 z inverse, and similarly plus alpha 2 times that, right? On top, plus alpha 2. The first way, the naive way, alpha 2 times that, okay? Let me just copy everything. Alpha 2 times exactly that. And these two things are forced to be equal, right? So we first assume that this decomposition is possible. And if it is possible, then this is correct, right? You can, again, reorganize everything, put the two terms back to one single term. And at the bottom, the denominator, of course, is that. But on top, we have alpha 1 times that plus alpha 2 times that. And they are forced to be equal to the original expression. So therefore, what should happen? Therefore, by forcing the equality, we realize that alpha 1 times 1 plus alpha 2 times 1 must equal to 1. And that's the constant term right here. And now we have a second equation. We will have two equations for two unknowns. The second equation is that alpha 1 times minus P2 plus alpha 2 times minus P1 must equal to what? Must equal to 0 because the Z inverse term does not show up right here. So this is what we mean forcing the equality. Okay? By forcing them to equal, so we have now alpha 1 times P2 plus alpha 2 times P1 must equal 0. And we already know P1 and P2, where P1, 2 is just 1 plus or minus square root of 5 divided by 2. So in principle, this is doable. Two equations, two unknowns. That's a naive way of finding out the coefficients. Okay? That's a naive way. So far, so good? So, are you convinced that this is doable, right? Even though the calculation might require really careful, you need to manage the numbers really carefully, but in principle, this is something that can be solved in a straightforward manner, okay? In principle, it is doable, right? So maybe let's go ahead and assume that we have found out after a certain algebra, you can find out alpha 1 equal to something, alpha 2 equal to something. Yeah. Let's assume that this is doable. But then maybe it's time to move on, jump to the next stage, next step first, okay? So once we perform this partial fractional decomposition, once this decomposition is performed, and once we figure out alpha 1 and alpha 2 in a naive way, the next step is quite interesting, okay? The next step is by looking at this, and again, forcing an equality to hold, okay? We are going to find another expression for these two terms, which are very similar, okay? So the first, what is that expression, the final expression that we need? The final expression of this is to understand that this looks like the sum, a formula for the sum of an infinite geometric series, right? This looks like a formula of the sum of a geometric series. If I write it down, you will understand what I mean. This looks like a formula for alpha 1 being the first term times 1 plus P1Z inverse plus P1Z inverse square and so on. P1Z inverse to the cube and so on, infinitely, right? Because this is indeed the formula for the first term. For the first term. Yeah, you might, there's a question to me that there are certain criteria for the equality to hold. This common ratio must have an absolute value of less than 1. Okay, let's worry about that later. But if this converges, it converges to this expression, right? So that's for the first term. For the second term, similarly, plus alpha 2 there, 1 plus P2 Z inverse plus P2 Z inverse square and so on, infinitely, right? If this power series converges, it converges to this expression. Yeah. So that's the kind of tricky next step, is to go for this change of expression and let's worry about convergence later, okay? Let's worry about, my suggestion, my recommendation is to not worry about the convergence at this moment. Let's not worry about it. But instead, we know that for sure, if this expression right here, if this geometric series, 集合级数嘛, geometric series, if this power series converges, it converges to this expression. Anybody against that? If this thing converges, it converges to this expression, right? Going from this direction to here is pretty straightforward. But now I invite you to try to just reorganize, rewrite this the decomposition into back to infinite sum. Okay, back to the infinite sum. And if you just allow yourself to do that, the benefit that now we have a general expression for if we start from h of z, right? H of z now is the sum of two terms. Now, h of z, if you organize everything here, we can let the index n go from 0 to infinity. Just put everything, just combine the two terms into one summation, right? So now what do we have? We have alpha 1 p1 what? Alpha 1 times p1 to the nth power plus alpha 2 times p2 to the nth power. It looks like we have this z minus n, right? Any correction? From here, it's rather straightforward, right? From here, you can just go one step further and merge the two terms into one summation, right? Can you help me inspect whether or not my expression is correct? Alpha 1 right there at the outside, right? So for every nth term we here have we p1 square, p2 square, for example. p1 square, p2 square, alpha 1 times alpha 1 times alpha 2, right? And so on. p1 to the cube, p1, p2 to the cube, right here with two constant coefficients now has been figured out right there. So everything has been figured out. So once you reach to, so far so good, is this all right? Looking good? Looking good? And then we are done. What's the question? Do you remember what question did we ask? What question did we ask? We want to find out the impulse response of this linear time invariant system, right? And then, long story short, in the end, we reach this expression of h of z. But what is h of z? H of z, by definition, is summation h0 n z minus n, right? That's the transform's definition. Where n, if this is causal system, n starts from time 0 for causality assumption. Based on causality assumption, we assume that the first term right here, the leading term is n equals to 0. From 0, and from 0 we sum to infinity, right? By definition, that's the definition of z transform of any of z transform, right? So now haven't we figured out the impulse response? Now we have a general expression of h of n for any given n, right? Can you see that? Now, by the last equality is because of definition, okay? And now we have two power series that are equal, and the only possibility is for every coefficient to be individually equal for any n. Okay? So therefore, we have the final expression h of n must equal to alpha 1 p1 to the n power plus alpha 2 p2 to the n power for any n greater than or equal to 0. So these are the few steps that are involved when we need to find out the impulse response to our particular example of a difference equation. Okay? So let me. So that's really the highlight of today's lecture. Okay? We learn how to solve the impulse response of that equation, of an equation by using Z transform, right? By using Z transform. Okay, so with that kind of a quick highlight, let's fill in some details right here, okay? So this is one key step with a leap of faith, okay? So I say it's a trick. We apply a trick for this following identity 恒等式 This equality holds as long as now we have the criteria is sufficient, and we have a sufficient criteria for convergence. Okay? So let's take a look. The equality hold that A alpha 1, for example, alpha 1 divided by 1, this expression equals to that. Same thing here. This expression equals to that as long as we have this assumption, okay, in a region, really. This equality holds in this region when Z is greater than the distance right here, when the distance of Z to the origin, when Z absolute value is greater than the absolute value of pk for this equality to hold. And here, so of course, I have done the calculation. So this is the kind of naive step I was talking about. Okay, by doing so, you'll be able to figure out alpha 1 and alpha 2. So it seems that previously I have helped you figure out, I checked it by myself, that alpha 1 turns out should be, let me fill in the number. Alpha 1, if you follow that naive way or a clever way, we'll share with you what is a more clever way. But here, anyway, the two ways to lead you to the same result. Alpha 1 should be 1 plus square root of 5 divided by 2 times square root of 5. Whereas alpha 2 is pretty similar, should be, there's a minus sign, minus, and 1 minus square root of 5 divided by, also by 2 times square root of 5. So that's alpha 1 and alpha 2 that can be figured out using one way or another. Okay, using one way or another, it's pretty straightforward, although you need to be careful for this example. So now, so this is what we talk about. After performing fractional decomposition, then we just reorganize the terms. We have that a general expression for h of n, which is the impulse response. Okay? Now we obtain a general expression for the impulse response for any given n. For any given n, this is the expression for h of n. Okay? All right. So for those of you that have encountered this difference equation, you know that we're talking about this difference equation is Fibonacci series. It gives you the impulse response should be Fibonacci series. So let's do sort of a recap. So recap is that we began with this difference equation. The current sample is sum of past two samples add any input that the system receives, okay? And after a long derivation, we are suggesting to you that if this system is a LTI system for sure, when receiving input, it produces output. And now, we're telling you that the impulse response, by definition, when the system receives delta function, unit delta function as the input, the output is what is called impulse response, right? Now we have suggested, we're suggesting to you now the impulse response has a general expression like that. Yeah? So let's put in everything. 1 plus square root of 5 divided by 2 times square root of 5. What is P1? P1 is this, right? That's P1. N power plus another term with what? 1 minus square root of 5. And there's minus sign in front. And then what is P2? P2 is, no, it's minus sign to the nth power. Okay? Any surprise? Any surprise? Have you been surprised? Who is looking at this result for the first time in your life? You have all seen the results? Yeah? Were you surprised at first? When did you encounter this result? Discrete math. You? Discrete math. Anybody from high school? High school? High school? Yeah. Which year in high school? Yeah. What was the first time you encountered this result? First grade? Like in elementary school? No. High school, good for you. Anybody earlier encounter of this result? I still vividly remember the first time I encountered result is the summer vacation when I was about to enter high school, senior high school. 升高一的暑假. I went to a pretty famous high school in Taipei. Yeah. I went to that and we got the admission, right? Somewhere in August we got the admission, and the school gave us like a set of like 100 math questions, and they told us that this is your summer assignment. Try to figure out. So those are the like most difficult questions ever that can be solved based on junior high school math. Okay, there are geometry questions, and one of the questions is to ask us to find out the general expression for exactly this. Yeah. So basically, I was surprised when I found out the expression because we know that what is Hn? Hn is 1, and then 1, and 2, 3, 5, and so on, right? Every term is an integer. So what surprised me is that even though every term is an integer, but then the general expression involves square root of 5. Irrational number, 无理数. Okay, so that's what surprised me at first. Okay? So I invite you to get back to the moment when you first encountered this equation, and there's a surprise. Okay, there's a surprise. I'm pretty sure when the mathematicians first discovered this general expression, they must be surprised too. Mr. Fibonacci must be surprised, must have been surprised. Okay? Every term is an integer, but the general expression involves the things right here. Okay, but anyway, we know that this is you can check every step along the way. So this is correct, and so here, anyway, so we know that from here to here, this equality holds only if both terms converges back to that, right? So this equality holds with a condition. As long as z is outside this distance, and z is also outside that distance. Let me write it down. So this part, equation 6, okay? This is equation 6. From the fractional decomposition back to the geometric series, the equality holds only if two criterions are met, okay? So here is a comment. Yeah. Equation 6 holds over the region of z must be greater than that, and z absolute value must also be greater than that for both expressions for both power series to converge to the fractional decomposition right? So for both series to converge, we need to require that equation 6, we can proceed to equation 6 only in the region of z greater than both of that, okay? Is that clear? So here, let's draw a picture maybe. So we may have the z-plane with real part and imaginary part. And on one side, we have P1 equals to that 1 plus square root of 5 divided by 2, the golden ratio, by the way, okay, 黄金比例. What is P2? P2 is actually negative. Have you realized that? 1 minus square root of 5. So P2 is negative. But anyway, P2 is negative, but it's right here. Something like that. P2 is negative 1 minus square root of 5. Okay, so there. So now, draw a circle, okay? You can draw a circle with that radius of P1. And you draw a circle, another circle, with a radius of P2, absolute value, okay? This is absolute value P2 for the radius, and this radius is absolute value for P1. Yeah? You draw two circles, and then we know that equation number 6 on the previous slide, equation number 6 hold only in a region where z is outside these two circles. Okay? So the region of convergence is outside the larger circle. Okay? The region of convergence is outside the larger circle, the larger among the two, for this example. This is the region of convergence. Region of convergence for what? For this equality to hold. Okay? So that's equation number 6 on the slide. Okay? For this equality to hold, we need to agree, z needs to be outside both circles. So that is to say, z must be outside the larger circle. Okay? That's the region of convergence for this equality, for us to go back and forth between here and there. Is that clear? So if we can agree on that, so that's what I've been saying. So z, in this case, z greater than that radius on the complex plane is called the region of convergence, or ROC. Okay, not kidding. ROC, Republic of China. Yeah, region of convergence for this causal system. And the next thing now addresses Fourier transform and stability. Okay, remember that we said that we want all the roots to be. One thing at a time. Yeah. Anyway, so let me finish this first. Okay. So now note that if I ask you, does the region of convergence include the unit circle? That's the next question. The region of convergence right there. Does that include the unit circle? The region of convergence right there, outside the larger of the two circles. Now, that's the region of convergence outside, okay? And where is the unit circle? Unit circle is, because this is actually greater than 1, right? So the unit circle is a smaller circle right here. That's a unit circle. Somewhere right there. This is the unit circle with radius 1, unit circle. So does our region of convergence right here, does it include the unit circle? The answer is no, right? Because the region of convergence is outside an even larger circle, right? So the region of convergence in this case does not include the unit circle. And why is this important? So you think about it. In other words, Fourier transform of h of n does not exist. Fourier transform of this h of n of the Fibonacci series 1, 1, 2, 3, 5, 8, infinite series. This impulse response, if you attempt to calculate the Fourier transform, sorry, it doesn't exist. Okay? It takes a while to kind of integrate all the knowledge right here. So this is an example where we do have a closed form expression for a signal, right? But this signal does not have a DTFT. If you even attempt to evaluate the Fourier transform, that DTFT does not converge, okay? Or DTFT simply we say does not exist for this very example of a signal with closed form expression for sure. But sorry, the Fourier transform, we need to say the Fourier transform does not exist because the region of convergence, because the Fourier transform will, because the Z transform will not converge on the unit circles, that is to say, okay? The Z transform, that expression converges only outside a bigger circle, okay? So the Z transform cannot be evaluated on the unit circle. Therefore, what is Z transform evaluated on the unit circle? Z transform evaluated on the unit circle is a Fourier transform, right? So we say, just after integrating all the knowledge right here, we need to say, sorry, the Fourier transform simply does not exist. A Fourier transform does not exist, okay, for this system. You can implement the system for sure. It's rather simple to implement, but let's not talk about Fourier transform. Let's not talk about magnitude response. Let's not talk about phase response. Let's not talk about group delay. Because the Fourier transform simply does not exist, okay? The Fourier transform of 1, 1, 2, 3, 5, 8, this sequence as a signal, its Fourier transform simply does not exist, and it's okay, okay? Fourier transform does not exist for this example. Okay? Maybe we can take a break. Okay, let's take a break of 10 minutes and we will wrap up with this lecture. right. Okay, so time to resume our lecture. And so we have a few things that still need to be addressed. First of all, we haven't discussed a formal definition of what we mean stability. How do we define stability? That hasn't been addressed. 还没有处理啊。First issue. And second issue involves what is an alternative way of finding alpha 1 and alpha 2? As I indicated in the last hour that this way is quite naive. It's good, it's doable, but it's sort of naive. 有点天真啊. So then you should ask me, what is the other way? Is there any non-naive way, more smarter way of finding alpha and alpha 2? So let's do that first, okay? So now I'm going to share with you a better way, perhaps, for finding alpha 1 and alpha 2. And the rest should just follow. And hopefully we do get the same answer, okay? So let's go through a more clever way of finding alpha 1 and alpha 2. How do we do that? And the rest should follow exactly the same way, okay? Once we have this, we talk about the other way of finding alpha 1 and alpha 2, right? So let me use green. So now we have a sort of a smarter way, a smarter, more clever way of finding alpha 1 and alpha 2. So how do we do that? So first of all, note that HZ is decomposed into a sum of two terms. Okay? So to find out alpha 1, let's multiply both sides of the equation by a factor. Okay? Let's multiply h of z by 1 minus p1z inverse. Equals to, so we multiply 1 minus p1z inverse. Anyway, the h of z is 1 minus, remember, h of z has this expression, right? Then now on top, we do have that, yeah. So that's on one side of the equation, okay? But on the other side of this equation, we have alpha 1 after multiplication by this factor, plus alpha 2, 1 minus p1 z inverse, 1 minus p2 z inverse. No, this is stupid. Let me make a correction. So we're talking about both sides of this equality, okay? So on the left-hand side of that equality, after multiplication by this factor, we should get 1 minus p2 z inverse, or 1. So let me make that correction, all right? So that's a smarter way, we claim, for finding alpha 1. Why? Then, this is an equality, right? So now we can evaluate both sides of this. We can evaluate this expression at z equals to p1. Okay, now evaluate at z equals to p1 for this. Okay, we will now evaluate this expression at z equals to p1. So we have 1 divided by 1 minus p2 divided by p1. on one side of the equality, right? And then what is on the other side of the equality? On the other side of the equality, we have alpha 1, right? That's that. But how about this term? Do we notice that this term now vanishes? Because we are evaluating everything at the expression at z equals to p1. So that appears on top right here. So this thing vanishes, plus 0 alpha 2 divided by 1 minus, it doesn't matter anymore. Because we get a 0. Because we get a 0 for that. Yeah. So this term just really vanishes. So now we have a very simple, we jump to all we need. Alpha 1 is equal to that. Okay? So that's kind of a clever way of finding out alpha 1, and alpha 2 should follow similarly. Okay? So can I erase anything? So this is a naive way. We don't need a naive way anymore. Okay, naive. Let me erase that. So what is alpha 1? So alpha 1 now, therefore, alpha 1 equals to, it's basically P1 minus P2 and to divide P1 on top. So that is, what is P1? P1 is 1 plus square root of 5 divided by 2 divided by P1 minus P2, P1 minus P2, P1 minus P2. Therefore, alpha 1 is what? Therefore, alpha 1 is therefore alpha 1 is 1 plus yeah, therefore alpha 1 is correct. This is correct. Okay? So that's the trick. And alpha 2 can be found out similarly. Okay? And this is a little smarter. Okay? This is a little smarter than the naive way. So if you take a look, if you contemplate on this result, this is a little, not just a little smarter, it's way more smart. Do you get a feeling? Yeah, this is smarter, right? Can you agree with me? This is smarter? Or, yeah, you nodded. Why? Why is this smarter? So say wait, yeah. Why is this smarter? Because it's more intuitive. Okay, any comment? Why is this smarter than the naive way? Why is the naive way more stupid? any comment? Why is the naive way more I consider it to be a bit more stupid. Why? Any comment? Let me just know right or wrong. Anybody want to comment on that? Why is this more smart? Why is this smarter? Why is this smarter? Why is this smarter? Because I say it's smarter. Because the professor says so. No. Any opposition? No, this is stupid. The naive way is smarter. Do you have an opinion? Can you elaborate on if what is if what? Okay, so yeah. So let me see if I understand him correctly. So remember that we have a rather simple special case, right? But what if we are seeking solution for general y and back to the most general formulation. Back to the most general formulation, we have y and sigma, right? A, k, y, n minus k, where k goes from 1, plus sigma, similarly for the input part, input linear combination, bk, no, this goes from 0, x, n minus k. So we know that for the most general difference equation, you may, in this way, you get some opportunity to design such systems seriously, okay? You get to design a system up to like 12th order IR filter. So imagine that now, if you have a 12th order, you have like 11 coefficients, right? No, 12 coefficients, AK, and up to, who knows, however many coefficients BK. So in general, what you're encountering would be A of Z equals to 1 plus A1 Z inverse plus A2 and so on to, let's say, 12, okay? Suppose that you have a 12th order system. You have a 12th order polynomial, okay? Assuming that you can find all the 12 roots. But then to perform that fractional decomposition, imagine you have 12 terms right here, and you want to merge them in a naive way and find out like 12 linear equations to solve 12 linear coefficients. That's not going to be complex, okay? You can imagine that to solve that is much more way more complicated than this smarter way, okay? So this smarter way, long story short, it generalizes easier, okay? You can generalize from a second order system to any 12th order system, but still applying the same principle. Applying the same principle, multiply both sides of your equation by a factor like that, and then you figure out the corresponding unknown. Okay? It generalizes well to a higher order system. And in that regard, this is a smarter way than the naive way. Okay? So thank you for the comment. Yeah, think about that. Okay, so that's kind of number one thing. So the next thing we promised to discuss is the notion of stability. Yeah, so what do we mean a system being stable? What do we mean when we say a system is stable? So I do have a few comments to cover. So know that the Fibonacci series, this system right here is unstable in the bounded input, bounded output sense. In that, you can just obviously h of n, the input response approaches infinity when n approaches infinity, right? It just keeps growing. Yeah. So therefore, this system is not bounded input, bounded output. So this requires some explanation. Okay, what do we mean bounded input, bounded output? Yeah. So for that, let me elaborate. This is a potential point for confusion. Okay, so bounded input, bounded output means so here we need to clearly define what do we mean bounded input, bounded output. Definition, BIBO means, it means that if we have a system, any kind of system, and it can receive any kind of input and produce any kind of output deterministically. Give the input, producing an output, everything is well defined. So if we have a system like that, bounded input, bounded output means that for any xn that is bounded, let's say is bounded below c, a constant. 应该这样子。And so means that there exists a constant that is smaller than, that is a finite constant, such that for any signal, input signal bounded with this upper limit, the output is also bounded. So let's say phi d such that yn is smaller than d for any n. Okay? Yeah. That's a definition for bounded input, bounded output. Okay? So let me read it. We have a system which receives the input and produces the output. Okay? If the input is bounded, let's say for all n. If the input is bounded, then the output is also bounded by perhaps another constant, non-infinite, okay, which is finite. If a system satisfies this criterion, we say this system is, we describe this system as BIBO. Bounded input, bounded output. First in, first out. Bounded input, bounded output, okay, in this sense. And this definition sometimes could be there's a potential point of confusion, okay? You need to avoid by raising a special example, okay? So we are not talking about, okay, now you have a system, and for a certain input that is bounded, the system produces an output that is also bounded, okay? No, we need to read this definition as a general constraint, okay? This condition must satisfy for any possible x of n that is bounded. If for any possible input that is bounded, the system also is guaranteed to produce the output that is also bounded. Then, only in that case, if we can make sure that this is the case, then we call this system BIBO. Okay? So do not just use a special case to check whether a system is stable in the BIBO sense. Okay? Please refrain from using one single example to check stability. Because it's more how do you say? It's more, the definition is quite, 应该怎么讲? This definition is pretty strict, 蛮严格的啊. This definition is pretty strict. It needs to be this it needs to be satisfied for any bounded input. Okay, so do not use just remark. So the strict definition. The definition is quite strict, so avoid using special examples for checking. Avoid using special examples or your test signals. Avoid simply using a special example of your signal for checking. Okay. The boundedness of the output needs to be guaranteed for any bounded input. Okay? Needs to be guaranteed for any possible bounded input. So therefore, but now, with this definition, we can talk about whether or not our system right here is stable. The good thing about the definition being strict is that once you can get a counter example, then to find out that if you have, if you find any given example that is bounded input, but unbounded output, okay, then that system is unstable. Let me repeat that. So the good thing about the definition being strict is that if you want to check a system whether or not the system is unstable, then your job is easier. You get that? You want to check whether or not the system is not stable, that is easier. Why easier? Because you just need to find one example of bounded input, unbounded output. You can just find just one example, then that system is unstable. Is that clear? So it's easier to apply this definition in that way. It's easier to prove a system being non-stable. Okay? Just give me an example of bounded input, unbounded output. One example would be enough. Okay? One example will suffice. Will be enough. So let's, using this kind of recommendation, let's check whether or not now is this system BIBO. Is this system BIBO? The answer is, of course, not, right? Because we have shown that the impulse response diverges. That impulse response is the result of receiving and bounded input signal. Receiving delta as the input, and delta function is bounded, right? Delta function is bounded, but now the output the system produces is unbounded. Therefore, this system is not stable in the BIBO sense. Yeah, just use this definition to check whether or not the system is not stable. Okay, that's easier. So, therefore, long story short, so let's, if you agree, let's come back to the note. So we say that just because the impulse response approaches infinity, the system violates the BIBO definition. Therefore, we say the system is not stable in the BIBO sense. Okay, so that's the first comment. Second comment. Even though this system in Fibonacci tree produces Fibonacci sequence, it's quite fun to study, but let me tell you, in principle, we avoid designing a system like that. In principle, in the rest of the semester, we want to design a system that is BIBO stable. This is just fun to study, okay? Fun to study. We never design a system that's not non-stable. Okay? Rarely any in my career, because you don't want your system to overflow the memory to produce a numerical error like that. Always make every effort to make your system stable. Okay, so this is fun to study, but we don't recommend designing a system like that. Okay, therefore, to design a system, always we need to check whether all the poles are inside the unit circle. That is to say, when we given a difference equation, the first thing you need to check is whether or not any root of A of Z is outside the unit circle. And if any of a root is outside the unit circle, if any of a root for a certain J, okay, if any of the roots of AZ is outside the unit circle, then immediately we know that when we partially decompose H of Z into that, if any of this factor P is outside the unit circle, the corresponding sequence is going to be a geometric sequence that diverges. And that's something that we don't want it to happen. We don't want any of P to be outside the unit circle. Okay? Because if any of P is outside the unit circle, then when we go to, then that corresponds to a sequence of 1, P1, P1 squared, P1 cubed, and so on. It corresponds to this term corresponds to this sequence. So we want to make sure that the impulse response is bounded. So we don't want any of the P to be outside the unit circle. We don't want that. We don't want any of the P to be outside the unit circle. So that's a pretty important recommendation for us to keep in mind. Whenever you are given a difference equation, or when you design your system in terms of a difference equation, always check this. Always we check whether or not any root is outside the unit circle. If one of the root is outside the unit circle, then sorry, redesign. Okay, sorry, do not 验货. So sorry if your vendor deliver a system with the pole outside unit circle, give them a call and reject the offer. Okay, ask them to redesign. Okay, make a strong request. Make Make an objection. Okay, object their offer and tell them to redesign, because they give you an unstable system. Like passing to you a difference equation with a pole outside. Well, when I say pole, maybe I haven't. The root of AZ are generally called poles. Okay, So if you check if any root of the AZ is outside, that's bad. The system is unstable. Say sorry. Please give me another design. Okay, so that's how serious it is. That's how serious it is. Okay. So far so good. Yeah. So we covered the smarter way to find out the coefficient alpha 1, alpha 2 for partial fractional decomposition. And we also made some discussion about what do we mean BIBO stable, and kind of general rule recommendations to check the location of all the poles. They all need to be inside the circle, unit circle. Okay. Yeah. So maybe with that, we can have a in-class, not the quiz, but now, yeah, let's look at this together. This is a second, oh, by the way, before I do that, let me mention about the midterm. Okay, I forgot to do that. Yeah, let's take a break. Let's take a break. Now, so about the midterm, you are encouraged, or you're allowed to bring a cheat sheet, A4 double-sided, handwritten. Okay, A4 double-sided, handwritten. Please don't print it out. Okay, please don't write on your iPad first and then shrink your font and then print out. I'm afraid that's not allowed. Okay, just handwritten. I do believe that by bringing in the old way, handwritten A4 double-sided, we are fair. Okay, we're fair to everybody. And also, is that okay? Can we agree on that? Please tell everybody, to any of your friends who is not in the classroom right now. Break the news. The kind of rule is A4 double-sided, handwritten only. Okay, handwritten only. So, any question regarding the midterm next week? I also announced exams from the past 2 years, 2024, 2025. You can find them. Okay, the first midterm of the past 2 years have been posted on EE-class. Anything else regarding the upcoming exam? About seating, I already discussed with our TA right there, so they will tell you which classroom to go to, okay? Maybe according to your ID, so please respect to their assignment, okay? Who should come to this room, who should go to the other room, so that hopefully nobody's sitting right next to anybody else, okay? We need to have an empty space just for the exam to happen. Okay, yeah. Does that sound fair? Fair to everybody? Yeah, about next week's midterm exam. Okay, so 2 more slides. The second to last slide of this lecture goes with a sort of exercise. True or false, okay? True or false, let's take a look at together. Suppose now we have an LTI system with impulse response denoted as h of n, and the system function is h of z equal to b divided by a, where both b and a are polynomials of z inverse. Just the difference equation way, standard way of notation. Now, assume that our system is causal and stable in the BIBO sense. So I need you to work out together which of the following statements are true after this description. Okay, assuming the system causal, BIBO stable with all the notation like that. Okay. Okay, so the first statement. Are all the poles of the system inside the unit circle? If I tell you, if they tell us this system is BIBO stable, are all the poles inside the unit circle? Secondly, does the Fourier transform of H, does it exist? What is that? What the heck is that? Wow. No cell phone usage for midterm. If you do, please turn off your speaker. Use your earphones so only you know the answer. Okay. Yeah, does the Fourier transform exist? Thirdly, does Hn approach 0 when n goes to infinity? Fourth, and finally, does h of z converges over the entire complex plane? perhaps except at z equals to 0. Okay? Now, who want to comment on any one of this? Who want to comment on any one of this? Or let me tell you, if I remember correctly, only one is false. Only one is not true. Which one is not true? 1, 2, 3, or 4? The answer is 4. The answer is 3. Let's take a vote. Who thinks number 1 is probably not the wrong one? Number 1, wrong one. Number 2, wrong one. Number 3, wrong. Number 4, wrong. Okay, number 4, wrong. Yeah. So 后面这位 why is number 4 wrong? Yeah. Yeah, so we talk about region convergence, right? Yeah, so in principle, you have AZ, find all the roots, and find the one that is most far away from the origin. Yeah. Good. So number 4 is wrong. It's not true. Because in general, there is a region convergence. Okay? So let's just say now we have A of Z. Suppose that we need to find the location of the roots of A of Z. Okay, so A of Z. So usually we give a cross. Okay, so it could be complex with real part and imaginary part. So, or on the real line, that's okay. So on and so forth. Right. There are finitely many of them. And when we say, if I tell you the system is BIBO stable, that means all the poles are inside the unit circle. Otherwise, the impulse response diverges. Okay, so that means all the poles are inside. Let me change my notation. This is not good. Yeah, let me just say A of Pj, where j equals to 1, 2, 3, 4, 5, all the way into, if I remember, m roots. Okay, all the Pj are inside the unit circle. Because of the BIBO assumption. Okay, so everything is inside the unit circle. That means the unit circle includes all the poles in it. Okay? So first one is true. If it's BIBO, then all the poles should be inside the unit circle. Otherwise, it's not BIBO. No. So therefore, 1 is true, 4 is false. Okay? This is correct, this is incorrect. The region of convergence is, I was saying, you need to find among all the poles which one is more the farthest away from the origin. Okay, the one that is, let's say, if this one is farthest away, 1. So from this is max P J. Okay, then the region of convergence is outside that circle. Okay. And since every pole is inside unit circle, this is the unit circle with radius 1. Our region of convergence is outside the biggest circle, like that. Outside the biggest circle, like that. So that's our region of convergence. It is not everywhere. Okay, not the entire plane except z equals 0. This is wrong. Definitely wrong. Is that clear? The region of convergence is just anything outside. Not the entire plane. Okay, definitely not the entire plane. So that's the region of convergence, which includes the unit circle. Which indeed includes the unit circle. This is a unit circle that is in the region of convergence. The unit circle is in the region of convergence. So therefore, what can we say about the Fourier transform? Can we or can we not evaluate Z transform on the unit circle now? Yes, we can evaluate the Z transform on the unit circle. Okay, so therefore the Fourier transform can be evaluated. The Fourier transform is therefore sure h of e j omega equals to summation h of n e minus j omega n. That's the definition of Fourier transform from 0 to infinity if the system is causal to begin with. Okay, so therefore the Fourier transform of our impulse response can be evaluated. This summation converges everywhere with any omega in, let's say, minus pi to pi. On the unit circle, everywhere you can evaluate this summation. It converges, so Fourier transform exists. The Fourier transform of h of n exists given all these descriptions. Okay? With all these descriptions, the Fourier transform can be calculated. And then finally, does number 3 hold? Yes, number 3 hold because what? Because the solution number 3 holds because h of n shall have a general solution. Number 3, h of n should have the general expression of alpha 1 p1 n to the nth power plus alpha 2 p2 to the n power plus and so on. Maybe we have up to m of them, alpha m pm z to the n power. That's a general expression for h of n for all n greater than or equal to 0. So therefore, you look at it. If all the p's are inside the unit circle, of course, this expression converges to 0 as n approaches infinity, right? So it's bounded input, bounded. It's not only bounded, but it converges to 0, even stronger now. Not only it is bounded, but it also converges to 0. Okay? So there's a subtle difference now. So anyway, one way or another, you can convince yourself that indeed, with all these descriptions, h of n converges to 0 as n approaches infinity. Okay, now, so that's kind of exercise. Hopefully, this example, this exercise, help you grasp the ideas that grasp all the ideas that we introduced today. Okay, now. So anything else? There's one final slide I want to share with you. Okay. Now, finally, this is quite subtle, but let me say, when you are given a difference equation, do not let the time go backward. Use it appropriately, okay? Use it appropriately, okay? So this is quite subtle, but let's try to do a few steps. Okay, just still go back to the Fibonacci sequence, okay? Yn equals to that sum of past 2 samples plus any input that's received currently, okay? For all n, right? For all n. But from here, you can move one step by just moving your terms around like that, right? Is this wrong? Is this wrong? Is this wrong? Not wrong, right? If this is the equation we're given, then this you cannot say this is wrong, right? Just by moving these two terms to the left-hand side and keep y only one term on this side, now this is not wrong, right? Does anybody think this is wrong? It's not wrong, right? And it happens for all n, right? So let's substitute n by n plus 2, right, for all n, right? Now, if we substitute this equality, substitute n by n plus 2, then we have the following result. Anything wrong here? Is it wrong? So mathematically, this is not wrong, right? But wrong. But then this is weird. It's not wrong, it's just weird. So it seems to suggest that you can write a line of code like that, okay? One line of code where yn depends on future two samples. Mathematically, it's correct, but physically, this is something, not a line of code that can be implemented, unless we know the future, right? Okay, so my take is that, this is my interpretation, okay? Mathematically, this is not wrong. It's just that I don't recommend doing this. Because the interpretation is problematic. Now you have a line of code that seems to suggest that your current output should depend on future output, right? This line of code requires that the present output depend on future output samples, as well as the future input. Yeah, it hasn't get arrived yet. So mathematically, all three equalities are equivalent. But just in terms of computer, to implement as a line of code, this is something that cannot be implemented. Okay? So please, when you see a difference equation like that, just go with the most straightforward interpretation. Do not try to act smart and suggest to professor, I want to implement this. Mathematically, it's there, but it's just we don't recommend doing this. Okay? So long story short, we say perhaps the kind of unified way to explain this is that we do have these are the same equation, but the same equation defines the causal system right here, but it defines a non-causal system right here. Same equation. But the way we look at it is totally different. In here, the time goes forward. In here, the time goes backward. Okay? So most of the time, in most of our applications, the time goes forward in this course. So I recommend that when you're given a difference equation, just follow the tradition, okay? This is fun to think about. The same equation, after substitution and moving our terms around, you get the same equation can define a non-causal system. Same equation, therefore same Z transform, right? But the region convergence is different, okay? So, but anyway, so we will not discuss any of the example where time goes backward. Okay? We do, in this course, I don't do any discussion like that, okay? The time always go forward. So in this course, we will not develop any further based on this interesting way of rewriting the difference equation. It is impractical, in my opinion. Okay? Fun to think about, but then stop there. Okay. And so that's a comment I want to make. All right. So, but with that, that'll be pretty much everything I want to tell you for today. So that should be it. That should be it for this lecture. And with that, see you next week. Okay. See you next week, and please come back to the classroom for midterm exam. And have a nice break.